Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
Hi everybody, thanks for coming. The last session of the conference, so I appreciate you showing up. My name is Bob Steagall, and as I've said before, I have the privilege of delivering a few presentations this year in the Back to Basics track. Each track is about a single concrete topic like this one, which is about templates, and the idea is to produce content that covers important things you need to know to be a working C++ programmer in today's world. Thanks again to our Back to Basics track chair, Arthur O'Dwyer, for putting the track together, and John Kalb for the conference. As I said when I opened part one of this on Tuesday, this talk is intended to be at a very introductory level, as if you were seeing templates for the first time. So I'm trying not to show you a little bit of everything. Instead, I'm trying to show you some important things in more depth, the things I wish somebody had told me about when I was learning about templates many years ago. So hopefully you'll walk away with some important things that can help you learn more about templates later. So that being said, let's recap what we talked about on Tuesday before we move into the new material and some examples. C++ supports generic programming with the templates facility. And a template is a parametrized description of a family of some facility. So a class template is a parametrized description of a family of classes. A function template is a parametrized description of a family of functions, and so on and so forth. Now, a template is not a thing. A class template is not a class. A function template is not a function. It's a recipe for making things. A function template is a recipe for making functions. A class template is a recipe for making classes. And sometimes when people discuss these or they write about them online, the distinction is lost and confusion sets in, which is why in part one I tried to emphasize using correct terminology so that you could be clear what you're talking about when you're reading and learning and communicating. C++ provides 6 kinds of templates: function templates, class templates, member function templates, alias templates, variable templates, and lambda templates. And I got a question as to why I broke out member function templates from function templates. And it is admittedly somewhat of an artificial distinction that I've added for this talk. The rules for parameter argument type deduction are the same for both. The difference between the two lies in how names are looked up. Different rules apply to name lookup for invoking a member function versus a freestanding function. And so that's why I broke it out separately. Translation units. So in C++, the compiler thinks of the process of building a program as something called translation, and it's performed in 9 stages which are well defined by the standard. Phases 1 through 6 perform lexical analysis, and this is what we traditionally think of the preprocessor doing. The output of phase 6 is what's called a translation unit. And a translation unit is a big, long text file. It's defined as being the source file that you're compiling, plus all the header and all the source files that were include via include directives, minus any lines of code that were skipped by if-def preprocessing directives. So if you've if-def'd something out, that won't be included. If you've if-def'd something in, it will be. And all macros have been recursively expanded until they are in their final expanded form. Declarations and definitions. So you may recall previously I showed a slide that gave you a long list of things that the standard considers to be entities. And entities correspond to syntactical constructs, and some of those constructs represent things that are instantiated in our program. And entities can be named, and conversely, a name is an identifier that denotes an entity. For the purposes of this talk, every template has a name, and every template specialization has a name, and that name is formally known as a template ID. So when you see discussions online or you're talking with an expert about it and they say, well, here's something that applies to a template ID, you know what they're talking about. A template ID is the name of a specialization. A declaration is a syntactic construct that introduces one or more names into a translation unit. And a declaration can reintroduce a name. We're all familiar with this concept. If we create a function prototype, which is simply the declaration of a function, we can have that function prototype declaration in our code as many times as we want, as long as we don't change it in any significant way. And the compiler will just say, yes, I've seen that name before. You're reintroducing it, and move on to the next thing, right? A definition is a declaration that fully defines the entity being introduced. The standard has kind of a funny way of describing these things. It says that every declaration is a definition except when it's not, in essence. So for purposes of our talk, we talk about class template and function template declarations and definitions. I gave some examples in part 1. And effectively, a function declaration can be thought of as a forward declaration or a function prototype of a function template. Class templates can also have declarations that are not definitions when you do a forward declaration of a class without providing the body of a class. If you declare a function and you provide the body of the function, that's a definition. If you declare a class and you provide the body of the class, that's a definition. Some things are actually definitions and declarations, like when you create using a type alias. The declaration of a type alias is also the definition of that type alias. We talked about the one definition rule, and this is very important. And it's just common sense. A program has to explicitly contain a certain number of definitions for certain kinds of things. If you have a non-inline variable or a non-inline function, just sort of an ordinary non-template, non-inline thing, then that thing has to be defined exactly once across all translation units that go into the program. Otherwise, you get multiply defined symbol errors. For something that's an inline variable or an inline function, a definition is required in every translation unit that uses it. But because it's inline, it also means that multiple definitions are permitted. And so if you have an inline function, and we've probably all written inline functions, you know that that inline function gets defined. The body of that function appears in every file that you've included it. So that definition appears multiple times across all translation units that contribute to the program. And that's okay, because with inline, you're telling the compiler, this thing can be defined multiple times. Every time you use a class in such a way that a translation unit uses it in a way that the class must be complete, and by complete meaning the body of the class must be provided so that the compiler can retrieve some information that it needs to do its job, well, that definition of the class has to appear in any translation unit that uses it. And, of course, this makes sense. We have header files. We create classes that are not template classes, and we include them in many source files, which make many translation units, and that all makes sense. In those translation units, the compiler needs to see those definitions of that class so that it can do its job. And it's not multiply defined symbols. It's not a problem. It's just the way the language works. So the important thing to remember about templates is the rules for inline variables and functions, meaning they can appear multiple times across translation units, also applies to templates. And with templates, you don't actually have to explicitly say inline. You can apply inline to template member functions, if you like, of classes or inline function templates. But by default, anything that's declared as a template, except an explicit specialization, can be defined multiple times across translation units. So we talked about template parameters and template arguments, and here's my little diagram. Template parameters are the names that come after the template keyword in the template declaration. They're the names of the things. Template arguments are the concrete items, the names of the things that are actually substituted for template parameters to create a specialization. And we'll get to what a specialization is in a minute. So in this case, T1 and T2 are my template parameters, but string and double are my template arguments. Likewise, there's a distinction between the template itself. Pair and max are a class template and a function template, and pair and max are a class template specialization and a function template specialization. So we've talked about templates and specializations. How do you get from templates to specializations? We know that the template is a recipe that tells the compiler how to generate something useful, and a specialization is the useful thing that's built from that recipe. Well, we get from template to specialization via one of two possible paths. One is the path called instantiation, and one is the path called explicit specialization. So, as I said previously, a specialization is the thing you get when template arguments are substituted for template parameters. Instantiation refers to the process of the compiler generating a specialization from a template. And instantiation is an overloaded word. It can refer both to that process of generating the specialization, but it's also, people use it as a synonym for the compiler-generated specialization itself. So it is both represents the specialization and the process of creating the specialization. There are two kinds of instantiation. There is implicit instantiation and explicit instantiation. Implicit instantiation is the one that we experience almost all the time. This is when the compiler sees the name of a template being used and some arguments being substituted for parameters, and it just goes off and it magically makes the specialization for you. And you hear it referred to as implicit or on-demand or automatic instantiation. Explicit instantiation is the case where you've decided for some reason you want to tell the compiler exactly when and where you want the specialization to be defined. And so I showed you some syntax for how to do that, and we talked briefly about situations in which you might want to explicitly instantiate a template. So on the left, we have the case of the kinds of instantiation where the compiler is doing the work for you. It's the one that's reading the recipe, following the rules, and generating the specialization, which is, the thing that you want cooked. Explicit specializations, however, are different. They are specializations where you as the user have provided all of the implementation of a template with all of the parameters fully specified. What you're effectively saying is, in this case, I want the specialization for this template to look exactly like this when it has these certain template parameters. And usually you want to do that in cases where there's a performance gain to be had. And I have some examples, hopefully we'll get to them near the end of the talk, of explicit and partial specializations. So moving on to newer material, templates undergo a process called two-phase translation, and you may hear this term. They're processed really in two phases as they're being parsed. When the compiler encounters a template at the site of its definition, whether it's a function template definition or a class template definition, when the compiler encounters its definition, the first thing it does is it checks for correctness to the extent it can. It ignores template parameters. So it looks for basic syntax errors like missing parentheses or missing semicolons. It looks for names that do not depend on the template parameters, but which it does not recognize. So if there's a name that depends on template parameters, it ignores it. But if it sees another name that it doesn't recognize that does not depend on a template parameter, it will say, okay, that's an error. And it will also evaluate static assertions in the code that do not depend on the template parameters. So it's like a first pass check. It's looking for basic correctness. It's validating as much as it can, except for that stuff that depends on the template parameters. Because when it encounters the template definition, there are no arguments that have been substituted for the parameters yet, so there's nothing further that it can check. Now, when the template is instantiated, the template arguments are substituted for the parameters. The names in the template which depend on the parameters, whether directly or indirectly, are looked up to make sure the compiler knows what they are. And then finally, all parts of the template that depend on the template parameters and the arguments that went into the function or the bits that make up the class template, they're all checked again. And assuming that everything is copacetic, then the compiler will say, okay, I have now created a specialization for you, and it moves on to the next thing. So you may also hear a term called two-phase name lookup, and that's part of two-phase translation. And really what that refers to is the fact that in the first phase, the compiler checks the names that don't depend on template parameters, and in the second phase, it checks for the names that do depend on template parameters. So if you see that phrase, two-phase name lookup, that's what it means. Of somewhat related here, and I'm just bringing it up for the sake of completeness, types, complete and incomplete types. So types can be complete or incomplete, and there's a distinction there that's very similar to definitions and declarations. There are certain situations that require a complete type. The compiler needs to see the entire definition of a function or a class or function or class template. There are other situations where the compiler can do its work without all of the knowledge of the type. So incomplete types are generally things like a class type that's been declared but not defined, a forward declaration of a class or forward declaration of a class template. An array type that has an unspecified bound as like a parameter to a function. Void, which is always incomplete, and some other corner cases. Sometimes incomplete types will work as template parameters in your code and sometimes not. So for example, perhaps you're writing some kind of linked list or something, and you want to create a base type for a node, and it's sufficient for the compiler to know that it's got to do size of this. It doesn't need to know what the template parameter is. It knows that it's going to be a pointer. Whereas maybe you have derived from that an actual node value type, which includes the pointer because it's part of the base class, but which actually contains the value that's going to be stored. So, and actually that should be node base as the pointer there, not T. Sorry for that typo. It's not terribly relevant to everything that we're talking about today, but I thought I would include it for the sake of completeness. So at some point, we need to use the recipe, and we need to make an actual thing. And to make the actual thing, the compiler needs to be able to see the recipe. So how do we ensure that the recipe is visible when the compiler needs it to go and, make the cookie or whatever? Well, in general, the way basically all compilers handle it these days is we take our template code, that recipe, and we put it in header files. And I'm deliberately not covering modules here at all because they're still relatively new, and frankly, I don't understand them yet. And then we include those headers in the source files that need to use that recipe. So here's a quick example. I want to create this class called foobar, and my foobar class, it needs to use a standard vector as its representation, and it has this member function to add things internally. So it's very straightforward, and you can see that I've got my class definition, my class template definition of foobar here. I've got a constructor that will size it for me, and I've defined the add member function to take a T object and push it onto the back of the vector, right? So that is a class template definition. Now I want to use that. Well, I've got a source code file, file1.cpp, and so in that I'm going to include my foobar, and I'm going to include string and complex because I want to make foobars that contain strings and contain complex numbers. And here I'm just making a little type def to cut down on the amount of visual noise here. And so I'm instantiating a foobar of string and a foobar of complex float, and then I'm adding some data to them. And whatever problem I'm working on, this is terrifically meaningful. All right, so in this translation unit, the translation unit that comes out of phase 6 of file1.cpp, after the compiler is done processing this in phases 7 and 8, the translated translation unit contains definitions, actual code definitions of foobar of string and foobar of complex float. Now I've got another file, file2, and in this one I've got another function, f2, that uses foobars of strings, right? That translation unit will also have the same definitions of the foobar template instantiated with string arguments. And then finally, I've got my main class, which calls the functions from the two translation units. And when you build them with GCC, you might use a command like this to build them with GCC. So the important thing is that there's no ODR violation here. The compiler has treated the definitions of the foobars, the specializations, as, in effect, as inlines, and it's allowing multiple definitions of these specializations across translation units that go into a given executable. Now I'd also like to talk about something called value categories, and it's important, no matter what you're studying in C++, to understand value categories, and it can be very important when thinking about templates and template type deduction, which we're going to cover in a couple of minutes. So every expression in C++ has an associated type, and every expression belongs to a value category. And expressions are a cornerstone of the C++ language. They are the thing that provide the primary mechanism by which computations can occur. Computations occur because expressions are evaluated. Now, value categories are the basis for the rules that C++ has for creating and copying and moving temporary objects when evaluating an expression. So here's a little diagram on the right that you've probably seen. And the standard takes all expressions and says that all expressions fall into one of 5 of these value categories that you see on the right, the blue rectangles. The 2 in the middle layer, GL value and R value, are sometimes referred to as composite categories. The 3 on the bottom, L value, X value, and PR value, are what are sometimes referred to as core categories. So I'm going to go through and describe what they are and try to explain my understanding of what the standard says they are in a way that I hopefully will help you understand it as well. And it's funny the way the definitions kind of jump around, but after you understand them and, bang your head against the wall a couple times, they start to make sense. So let's start with the GL value. And this is informally means generalized L value. So a GL value is an expression whose evaluation determines the identity of an object or a bit field or a function. This means that a GL value is something that has storage. Because it has storage, it has a name that you can use to address it either directly or indirectly. And because it has storage, it has an address that can be taken. And the little asterisk there means except for bit fields. You can't take the address of a bit field. Non-const GL values can also be assigned to. And again, the asterisk is there because GL values, function pointers, functions are GL values, but you can't assign to a function. So basically, GL values is a generalization of the things that we deal with most of the time, things that have names, things that we can take the address of. A PR value, on the other hand, and PR is P is for pure, a pure R value. This is an expression whose evaluation is used to initialize an object or a bit field or computes the value of an operand of an operator. And so when the compiler is evaluating operations that involve operators, it will frequently create temporary objects as part of performing the evaluation. And so, as an example, those temporary objects are PR values. PR values, because they're pure, they have no name, they have no storage. An X value is an interesting case. An X value is a kind of GL value, but it doesn't include functions. It denotes an object or a bit field whose resources can be reused. And the X informally means expiring value. And what it means is it's a GL value, a thing that has storage, a thing that once had a name, whose value and whose name don't matter anymore. Okay? When you have a string S, and you do something with S, and then you want to take S and you want to move it into a vector. So you do vector, your vector is V. You do V dot push back, stood, move, S, right? What you're doing with stood move is you're converting that L value, that GL value S, to an X value. You're saying, I'm not going to use S anymore. Its value doesn't matter. It's now an X value. And then, of course, the pushback member function of vector will say, oh, this is an R value reference. I know what to do with it. I'm going to move the buffer out of string and use it. Right? That's the purpose of X value. Stood move creates X values. An L value, and then the last two are very simple. An L value is a GL value that's not an X value. Right? An X value is this very small portion of GL values, and an L value is a generalized L value that is not an X value. So GL value is the set union of L values with X values. R values, as a composite category, is the set union of PR values and X values, right? So it takes a little bit to wrap your head around this. And hopefully, I have some examples here, and hopefully they will help make sense. So really, when you're dealing with code, unless you're doing something really esoteric with functions and function pointers, and if we just confine ourselves to thinking about objects that we create, then L values are things like expressions that designate variables or functions. Class data members. They have names, they have addresses. Those are L values. A call to any function that returns an L value reference, like a const L value reference, a const reference to some internal member. You've got some internal member of some class that's big and it's too expensive to copy when you want to return it, but you want to give your class user access to it. So you return a const reference to it, right? That const reference is an L value. PR values, pure R values, these are things that have no names, things that you can't take the address of for the most part. Literals, like enumerations, simple enumerations, integer constants, floating point constants, these are things that have names, and we all have an intuition that you develop very early that you can't take their address. Those are PR values. When the built-in arithmetic operators generate temporary objects as they're evaluated, those temporary objects are pure R values. A call to a function that returns a non-reference type, a function that returns something by value, that by value thing that's returned, that's a pure R value because it doesn't have a name. And as I mentioned before, X values are things that you don't care about the value anymore. And for the most part, this is when a cast is made to an R value reference to an object type. By casting it to an R value reference, the thing that receives the R value reference says, oh, this is an R value reference. This thing is an R value. You've just told me I'm free to steal the resources out of it. So the idea of X values and how they interact with R value references is what allows us to have move semantics in C++. Okay, so I'm going to dig into function templates and class templates in a little more detail. I've got a lot of examples, not as much words, and hopefully it will make sense. I'm going to spend a good amount of time on template argument deduction because I think it's very important, and I hope that the tables that I made will actually help you understand it. So there's a little bit of an experiment going on here. So let's talk about function templates. A function template's a recipe for generating a parametrized family of functions. All right, we know that. Well, here's an example of a function template, min. All right, this is a function template. It's not a function. It can't do anything. But it can be specialized, and the specialization can execute code and do computations for us. So here we see I'm invoking min, and in this invocation for S2, I'm explicitly specifying the template parameter. I'm saying do min for string. For S3, I'm allowing the compiler to decide what the template argument is. And in this case, it will deduce that the template argument is string. This is the way we normally use things like max and min. We let the compiler figure out what the template argument is supposed to be. Here's another example. Here's an example using double, and it's exactly the same thing, except I'm explicitly specifying double as a template parameter for template argument for D2, and for D3, the compiler is looking at a double literal 2.78, and it's also looking at D1 and saying, yeah, these are both doubles, I understand this, I'll make a specialization for double. Okay, so here's our definition again. All right, so here we've got I, which is 42, and D, which is 3.14. I is clearly an int, and D is clearly a double. Now, I tried to do the min of, well, that should be I and D. Typos. All right. So I'm trying to do the min here of I and D, so, mentally do some substitution here. But this is an error. The compiler will flag this as an error because it doesn't know what the template argument is supposed to be. Is the template argument supposed to be an int, or is the template argument supposed to be double? Both are equally likely. So the compiler says, yeah, this is an error. Won't let it compile, right? Can't promote. No. Promotion never plays a part in template argument deduction. So to resolve this, in this particular case, I just said, okay, well, I know I want double, so I'm going to explicitly specify that double is the template argument. Now in this case, because I've explicitly specified it, then the template knows what these function parameter types are supposed to be. The function parameters are both supposed to be const references to double, and in this case, the D matches perfectly, and the I will promote, because int to double is a trivial promotion. So that will work. So in general, let's think about an example. In this silly example, I've got a function template that has 3 template parameters and 3 arguments, right? Just totally made up, doesn't mean anything. How does the compiler determine the types T, U, and V? I'm calling the function f here, right? And so that's an int, that's a double literal, that's a string. But how does the compiler actually know what those are? Because I could have much more complicated types that I'm passing as arguments. So template argument deduction, this is the process that the compiler goes through to determine the type of the function template parameters based on the argument types. It's fairly complex. I'm not sure I could explain it even in an hour, so I'm going to try and hit the basics, the most important parts of it. So the way to think about it, or one way of thinking about it, is let's just consider a single template parameter with a very simple function. And so here we've got our function f, so we've got a template parameter t, and we've got sort of 3 things that can vary here. We've got this parameter type, we've got the way that we invoke f, and we've got some expression, right? So this is the function, so we have a template parameter, we have a function parameter, we have a function argument, and we have an invocation of the function. So given the form of the invocation and the type of the expression that's passed as an argument, a function argument, the compiler has to figure out what is parameter type? What is the parameter type of the function? And that will be, the type of the function argument t, the type that's represented by some expression. And it needs to figure out t, which is the type of the template argument. So parameter type and t are not necessarily the same thing. Consider the case that parameter type is string const ref. Well, then we all have the intuition that t would, and you pass it a string, s, then we all have the intuition that the template parameter, capital T, would deduce to string, because that fits the pattern. So the compiler undergoes an extensive process of pattern matching, trying to figure out what you, as the programmer, intended to do. So all of the template parameters, in the case where you have a function that has multiple template parameters, they all get deduced in parallel. There's no crosstalk between them. They're all deduced individually. So let's take the case where we are, the simple case, we are explicitly specifying a template parameter, right? That's the easy case. That's the first thing the compiler looks for. So it's very simple. Explicitly specified template arguments are fixed as specified. The deduction is trivial. You specify that a parameter is a foo, then I deduce that the parameter is indeed a foo, and I move on, right? And we've seen some examples of this. However, if we don't explicitly tell it what the type is, then we go through a more extensive process, a sub-process of type deduction, which is called type inference. So in these examples, I'm not explicitly saying what the template parameters are. The compiler has to figure out what the parameter is for each of those function calls. And it's just a wall of code that I threw up there to show you that, there are many different ways that arguments can be passed, and the compiler needs to figure out what is the template parameter type, capital T, for all of those things, so that it can correctly create the specialization that's going to go and do something for us useful in the future. Okay, so what are the possible forms, syntactic forms, that parameter type could have? Well, here is a list of most of them. You'll notice that I'm leaving out volatile because it just doubles the amount of code that we have to consider and is not sort of falling out of fashion, is beyond the scope of this discussion. You'll also notice that I don't have tconst there, and the reason I don't have tconst is because the compiler deduces tconst as t anyway. All right, so t, you can have a pointer to t, you can have a pointer to const t, a ref to t, a reference to const t. You can have an r value reference to a t and an r value reference to a const t. So these are the various forms that parameter type can take, the various syntactic forms. What are the possible types that expression can have, the actual thing that's being used, the actual function argument there? And I'm going to assume here that we're using int. Int is in there somewhere because it's a very short name to type, right? Well, the type of some expression could be int, it could be int const, it could be a pointer, a const pointer, reference, const reference, it could be an r value reference or a const r value reference, right? All of these kind of things occur, and again, I'm assuming int here because it's easy to type and there's not much noise there. All right, so what I've done is I've created this table to show you what the deduced type t is. Now, on the left, this is the actual type of the argument of some expression that's passed to f. And along the row are the various syntactic forms that we just looked at. So the question is, when the compiler encounters a type of expression like this, and our parameter type has one of these expressions, what is t, what is capital T deduced to be, right? So what we have to do, what the compiler does, is it takes the actual type in the row on column on the left, and it substitutes it in for the t, almost like a textual substitution, right? And when it does that, it does something called reference collapsing, which you may have heard of. So what is reference collapsing? Well, let's step back. We probably all have the intuition that you can't declare a reference to a reference, right? If I have an int const reference, I can't do this. I can't say I want a reference to a reference. That's an error, right? But when the compiler is substituting one type for another, that kind of thing can occur. So the compiler needs to have rules for how to figure out what the result is. And there is certain reference collapsing that's been around since the beginning of templates. So when the compiler is composing types, it composes references according to certain rules. All right, and so here are the rules. You have a function, an expression that's a reference, when combined with a parameter type that this reference, collapses to a reference. And a function, an expression that yields a reference when combined with a parameter type that's an R value reference, collapses to a reference. So basically, you have the number of ampersands that are part of your expression, and you have the number of ampersands that are part of your parameter type. And you take the minimum. That's one way of looking at it. But here's some examples. Let's suppose I create this type def ri, which is a reference to an int. So I'm going to make an int 42, and I'm going to create a reference rx, and I'm going to assign my value to rx, right? Now, suppose I want to use ri, and this is very analogous to a template parameter. I want to create a const reference to ri. Well, ri is already an int reference. But you'll note that I, as a programmer, have not written two ampersands here in a row. Instead, I have this indirection here with ri. So what does the compiler do? Well, the compiler says, okay, well, ri is int reference, and I've got this pattern, ri const ref. So it puts together this string, int ref const ref. And then it drops the outer const, the one on the right. It's then left with two ampersands, which it collapses to one, and the resulting type of rrx is int ref. That's an example of reference collapsing. Here's another example. Suppose I have a type alias called rci, which is a reference to a const int. And now I have rci, and rci could be a template parameter. And so I've got some syntactic construct that has an R value reference after it, and I want to do some assignment. Well, what the compiler does is it takes int const ref, which is rci, it builds this, and then it adds the, I'm sorry, there's another typo there. It should be int const ref, ref, and then it collapses the ref and the ref to one ref. And you end up with rcx as an int to const ref. I'll fix that typo. And similarly, here we have a case where rri is a ref to int, and we want to create a const ref to something which is a ref. And again, the compiler puts this construct together internally. It drops the outer const, it combines the two refs, and leaves with one R value reference. And the result of the reference collapsing is that you have int ref. So this example that I've shown right here is very, very similar, and this is actually from JUCE and Van de Voorde's book, where it's explaining how it works outside of templates. But the compiler goes through exactly the same process when it substitutes types in for template parameters. So let's go back to the table and try to go quickly column by column. So here, we've got a template parameter type is t, and these are the types of the things that we're passing to it. In all of these cases, the compiler is going to deduce that, yeah, this is an int, except for the case of pointers. For the case of pointers, the compiler will say, well, you know, the type that you're passing me is an int const pointer, therefore t must be an int const pointer. Whereas if we look at the case of, say, t const ref, I pass it an int const, and I put int const into this pattern, the compiler says, well, you plugged int const into here. There's two consts in a row. I'll drop the const, therefore t is an int. It's a pattern matching algorithm. So you can use this table to figure out what the type of t is going to be given the expression types on the left and the parameter type. What I did want to point out, however, was the column on the right. Now this is a very special form which is called a forwarding reference, and it has special matching rules. This is the case where it solves the perfect forwarding problem, and it's called, you've probably heard it called a forwarding reference before. And so what happens is there's a very special rule. So let's look down here at the case of I have an int reference, and I have a reference to an int and an R value reference to an int. Those are my two expression types. Now, my parameter type is tref. And so what happens is the reference collapsing rules here will say, okay, well, I have an int ref, and my reference collapsing rules say, well, I'm going to collapse a ref and a ref, and I get just one. So it's a reference to an integer. But in this one case, in this one column, if I have two R value references, it gets stripped off and it deduces only the bare type. And there's an analogy here with int const ref and int const ref. In the case where it's an L value reference, it deduces an L value reference. In the case where it's an R value reference, it deduces the bare type. Down here, in the case where the expression is an L value reference, it deduces an L value reference. In the case where it's an R value reference, it deduces the raw type. This special change for this one kind of template parameter is what allows us to have perfect forwarding, so that you can call stood forward on some object with the correct template parameter types and have it perfectly forward through any chain of function calls. It's what allows you to perfectly forward literals, or perfectly forward R value references or L value references, and maintain their PR valueness, their X valueness, or their L valueness through a chain of calls. This special rule, combined with the magic of stood forward, is what allows that to happen. Okay. I'm just going to go quickly through this slide. So we've seen how individual arguments are deduced, but there's a lot more to it. And informally, there are several steps. I'm running short of time, and I'm not going to discuss all of them, but they're here. The most important ones are explicitly specified template arguments are fixed as such. And for arguments that are not explicitly specified, the compiler goes through the process of type inference and tries to figure out what the associated template parameter type t is. If it can't do that, then it looks for a default argument for that template parameter. And if it can't find that, then it's an error. All right. Return type deduction very quickly, moving on to another topic. Sometimes the compiler can determine the return type. So here, I've got a very simple min class template, and I can also rewrite this template in such a way that I allow the compiler, through the magic of auto, to determine what the return type should be. And the difference between the template at the top and the template at the bottom is the two templates at the bottom allow me to compare two different types. And in this case, the compiler, through its deduction rules, will look at this and it will figure out what is a common type that can represent both A and B. If you're familiar with the traits type, stood common type, that's part of the type traits library of the standard, this definition of min is equivalent to this. And basically what this is saying is the compiler looks at the type, deduces the types of A and B. It figures out, is there some type that's capable of representing both? And if so, I will return the value of the result of this comparison in that type that's big enough to hold both values. So if you compare an int and a double, the result's going to be a double. I talked before about how function templates could be explicitly specialized. This is just a quick example of that. I wanted to move on quickly to class templates. So let's write a simple stack adapter. And I'm writing my own stack because I have some special things I want to do with it. So I'm going to put this in a header, very simple interface. I'm going to use a vector as the representation. I have some very simple member functions. So let's talk about template parameter scope. Capital T, which is a template parameter, where is it meaningful? Well, the scope of a template parameter T begins right when T is named. And the scope of capital T ends at the bottom of the class definition. So anywhere between those 2 points, capital T means this template parameter. What about defining member functions? Well, of course, just like regular classes, you can define member functions inside the body of the class, and they're implicitly in line if you do that. But you can also define them outside the class. So the question becomes, where is the scope of the template parameter active in this case, where you have an out-of-line definition? And again, the scope is when T is first introduced to the end of the function declaration. So just in this region is capital T meaningful. So let's add a new function, push all from, and I want to push all the values from some other stack onto this stack. So inside the class definition itself, can I just use stack the name, or do I have to use stack T? Both are equivalent, both are proper inside the body of the class definition. Most people don't use the template parameters because it's just excessive visual noise, especially if you have multiple template parameters. It can be either inside class scope. And just to be clear what class scope is, class scope begins at the left curly brace and ends at the right curly brace. So this could be a definition of push all inside the class declaration. And I want to return a value of the old stack, so I make a copy of the current stack, then I use the insert member function of the vector to insert all the data from the other stack onto the back of this stack, and I return the old one, right? What about if I want to define this member function outside of the class? Well, if I'm outside of the class, why do I have to use stack angle brackets T here? If you don't use stack angle brackets T there, the compiler will complain for many hundreds of lines, right? So why do you have to use it here, but not here? And the reason is because these stacks are not yet in class scope, but these stacks inside are. So with member function definitions that are outside the class body definition, class scope begins at the colon, and class scope ends at the right curly brace. So that's why inside the body of the function, you can refer to stack without the template parameters. But before the colon, you have to use the template parameters. All right, let's suppose we want to have some iterators, and we want to iterate from our stack from top to bottom, right? All right, and we want them to be const iterators because we don't want people changing the contents of the stack. So we'll copy what vector does. We'll create this thing called const iterator, and we'll do begin and end. Well, where does const iterator come from in this example? Well, we want to do something with the iterators that vector already provides. We want to use them from vector, but how? Well, because we want to traverse the stack from the top of the stack to the bottom, and we know our vector is keeping the top of the stack at the end of the vector, we want to use a const reverse iterator. And in our implementation, that will get us from the top of the stack down to the bottom. All right, so we might say, all right, well, we'll just reuse the reverse iterator that vector defines, right? So we type this and we go to compile it, and no. Compiler says, no, that doesn't work. Why doesn't it work? It says you're missing this thing type name prior to a dependent name. So stack const iterator is what's called a dependent name. It depends on one or more template parameters. So it depends on the template parameter through vector. Vector of t depends on the template parameter t. And all of the nested type aliases that vector provides, like const reverse iterator, by transitivity also depend on t. So that means vector of t const iterator is a name that depends on the template parameter capital T. And therefore, our const iterator depends on that dependent name. So fortunately, the way we fix that is we add type name. And this use of the keyword type name, this is the second use of keyword, tells the compiler this thing, vector of t const iterator, this is, I promise you, this is really the name of a type and it really exists, and will you please use it like it's a type? And it will. This resolves the problem. But in the case where the thing that you're trying to alias or use depends on the name of a template parameter, you'll probably have to use type name to resolve that ambiguity. All right, so we can implement our begin function inside the class. We can also implement it outside the class, but we'll notice outside the class, we're outside of class scope here for the return type, so we also have to use type name here, because outside of class scope, stack t const iterator is a dependent name to the outside world. So we have to tell the outside world that, hey, this dependent name, stack t of const iterator, I promise you it's really a name of a type, please use it as such. And this will work. However, the nice clean syntax and the way to get around that is to have a return type auto and then just use the trailing return type and use const iterator here. And this works because I'm after the scoping operator, so I'm inside class scope, and inside class scope I've already declared const iterator and the compiler knows what it is. Those two definitions of that member function are entirely equivalent. What about static data members? Ordinary classes can have static data members, and so can class templates. So here's the way you might do it traditionally. Say I want to keep a count of the number of instantiations, so I declare a static int. And then before C++17, I would have to define storage for that outside the template using syntax that looks like this. And you could put that in a header file and it would be okay, because the compiler says, yes, this is like an inline thing. It can be declared, it can be defined multiple times, and I'll figure it out for you at the end and make sure only one is defined. You don't have to worry about that. Since C++17, it's very useful. You can declare static variables inside the class body as being inline, and you can define them right there. It's very nice, simple syntax. It does exactly the same thing. It makes sure this static int variable mCount is defined exactly one time for every template parameter where stack is instantiated. Suppose we want to customize our stack specifically for ints for some reason, right? Well, we can create a full specialization of stack, and here my full specialization of stack for int has a completely different interface. And here I want to push int, and for some unknown reason, I want to push the characters from a string. I can do that because this is a full specialization of the template, and I have the freedom to make this particular specialization for int anything I want it to be. And so if I wanted to, I can define push from inside the class. I won't show you that because it's trivial. Outside the class for a full specialization, however, I just wanted to show you the syntax for that. Here, it's as if this was almost not a template. There's no template decoration here. There's no template angle brackets. It's just the void stack with the template arguments right here. And that's how you would define a full specialization for a class member function out of line. Now, because this is a full specialization and it's defined out of line, it's not a template. So it's not inline. This definition is not an inline definition because this is not a template. This is a full specialization. So if I wanted this thing to be inline, I would have to prefix it with the inline keyword. So what about if we wanted to customize our stack for pointers, but not a specific kind of pointer, any kind of pointer? Well, we would use something called a partial specialization. And so what I would do is, in the definition of my class, I would have my template parameters, but then I would say, I'm creating a stack for pointers of t. And the compiler will do pattern matching and say, oh, your template argument is a pointer. Okay, I'm going to use this template thing. And the reason I want to do this is because I want to have special semantics for pop. Instead of pop being void, I want to be able to pop the pointer that's on the top of the stack so I can delete it, right? So for any time I have the template argument is a pointer, this partial specialization is the one that will eventually be instantiated. And so here, the syntax for an out-of-line member function for a partial specialization includes the template decoration at the beginning, and of course the return type, and then the body of the function, where I create a temporary, I pop it, and I return the pointer. So with the partial specialization, I still need to have this template decoration at the beginning. You can also, partial specialization uses a kind of pattern matching. So suppose I have a simple pair class. Now, I suspect that my users might be using references as template parameters, but I actually want to store objects inside. So what I can do is I can create partial specializations for when t is a reference, but u is not, for when u is a reference and t is not, or for when t and u are both references. And in all of these cases, I can force the internal representation to be the same. So if for some reason, they pass me a string ref, I can still store a string inside. What else can we do with partial specializations? I promise I'll wrap up in just a couple minutes here. We can detect type properties of types as predicates. So here, I want to determine if a type t is a pointer. So I can create this traits class. So it's a struct. Everything's public for ease of use. And inside this is the primary template. In the primary template, by default, a type t, I'm going to create an internal value, and I'm going to say, yeah, this is false. In general, t is not a pointer. Then I'm going to create a partial specialization for this structure, and any time that it matches a pointer, well then the internal Boolean is going to be true. And then I'm going to use a template type alias, which I covered on Tuesday, and I'm going to create this alias called isPointerV. And isPointerV, I'm going to assign it to the value of isPointerT, right? All right, so why do you do this? Well, suppose I have some function template foo here, and foo takes a t. And I want to do one thing if t is a pointer, and I want to do another thing if t isn't, because there's some optimization that I can employ. So I can use if const expr, for example, in this, and I can check the nested value of the Boolean, or I can use this template, this alias template. These two syntactic forms are entirely equivalent, and at compile time, the compiler will pick the branch of code that matches the compile time value of this traits type, and the other code won't even be generated. So here I'm doing a kind of type detection. I'm creating a predicate based on some property of a type. I can also normalize properties of types. I can remove, for example, const ref qualifiers. So here I have remove CV, and I have a type result, a nested type alias, which tells me what the result of this template meta function is. In the general case, the type with CV removed is t. But I can use a partial specialization to catch the case where t is const, where t is volatile, or where t is const volatile. And in all four of those cases, I can strip out the CV qualifiers and just have the base type be t. And here I'm creating a type alias that is an alias, a type alias for this nested type. It can do something similar for remove ref. Here I'm removing references, so I've got the base type, which has no reference. I'm removing an L value reference and an R value reference. And I'm creating another type alias for that. Why in the world would I want to do this, right? Well, I can go through, I can use this type traits from the standard called isSameV, and I can check that if I remove CV from int const, and I'm removing the const, I get int. If I've got int const ref and I remove the ref, I get int const. I can combine them. I can take an int const ref, I can remove its ref, I can then remove its CV, and then I can get int. All right, so what? We can use traits like this to improve the implementation of our stack. And the way we do that is, I don't trust my users, and I want to make sure whatever type they pass, if they're passing me some weird reference type, I want to strip the reference off of it, I want to strip the CV qualifiers on it, and I want to use that unadorned, bare, base type as the element type in my stack. This is one possible use of type traits in this way. All right. Very quickly, templates can have friends. So here I've got our stack. I've decided that every other stack of a different parameter type, all of my cousins are friends of me. Also, the regular class foobar is a friend of me, and the template parameter t is a friend of me. So all of these things have access to my internals. And you can also have friend functions, ordinary functions and function templates. All right, summary, wrapping it up here. C++ templates are a vast, vast topic. And here are some recommendations. Start simple, try to understand the value categories, understand function templates first, and then learn type deduction. Understand overload resolution and how it applies to function templates. Once you've mastered that, the rest is actually quite easy. Then move on to class templates, learn how partial specialization works. It's an incredibly powerful tool. Try writing some of your own type traits, like the ones I just wrote. Get Vandervoort, Jasutis, and Gregor, read it. Watch any talk about templates given in the last 10 years by Walter Brown. They're extremely well researched, extremely well done. Use CppReference.com. I have it open on my desktop constantly. Ask questions and don't give up. And thank you for your patience. Sorry I ran over.